Picture standing at the edge of the universe, staring into an abyss so powerful it twists the very fabric of reality around it. Light cannot escape its grasp. Time itself slows to a crawl. This isn't science fiction, it's the heart-stopping reality of a black hole, nature's most enigmatic phenomenon. And today, we're traveling back to where it all began, the first black hole ever discovered, a cosmic mystery that rewrote our understanding of space and time. Think about the audacity of that moment when scientists first realized they were staring into the void. No telescope could see it directly, no instrument could touch it. Yet there it was, a silent predator lurking in the darkness, bending the rules of physics as we knew them. How did humanity even begin to unravel such a mystery? What did it feel like to stand on the precipice of that discovery, knowing you'd found something that defied imagination? This is the story of that first black hole, not just as a scientific breakthrough, but as a testament to human curiosity. It's a journey that will take us from the chalkboards of Einstein's equations to the far reaches of space, where stars collapse into nothingness and gravity becomes a force beyond reckoning. Along the way, we'll meet the brilliant minds who dared to ask the impossible questions, and we'll uncover why this discovery still sends shivers down the spines of astronomers today. So buckle up, we're about to dive into the unknown where the laws of physics break down and the universe reveals its darkest, most mesmerizing secrets. To understand black holes, imagine the universe as a vast cosmic ocean. Now picture a whirlpool so strong that anything drifting too close gets sucked in. No escape, no second chances. That's essentially what a black hole does, but instead of water, its pull comes from gravity cranked up to unimaginable extremes. At the heart of this phenomenon lies the singularity, a point where matter is crushed into infinite density, warping space-time so severely that even the rules of physics start to break down. Surrounding the singularity is the event horizon, the point of no return. Think of it like the edge of a waterfall. Once you cross it, there's no climbing back up. Light, rockets, even your fastest thoughts, nothing can outrun the pull once it passes this invisible boundary. That's why black holes appear black. They devour every shred of light that ventures too close, leaving only an eerie darkness where stars should be. But here's where it gets even wilder. Time near a black hole doesn't behave the way we're used to. If you could hover just outside the event horizon and somehow resist being spaghettified by gravity's stretch, you'd witness time slowing down dramatically. A single minute for you might feel like years for someone watching from afar. It's as if the black hole bends the very fabric of reality, turning the universe's rulebook into a suggestion. And yet, for all their destructive power, black holes aren't cosmic vacuum cleaners mindlessly sucking up galaxies. Their pull is just like any other gravity, stronger when you're close, weaker when you're far. Our solar system could orbit a black hole the same way it orbits the sun, as long as we keep a safe distance. It's a reminder that even the most terrifying forces in the universe play by elegant, predictable rules once we dare to unravel them. Long before telescopes could peer into the depths of space, before anyone had proof these cosmic monsters existed, a handful of brilliant minds dared to predict the impossible. The story begins in 1783, when an English clergyman named John Michell, who also happened to be a groundbreaking scientist, penned a radical idea. He imagined stars so massive and dense that even light couldn't escape their gravity. He called them dark stars, and though his calculations were crude by today's standards, the seed was planted. The universe, he realized, might hide invisible traps where gravity won the ultimate battle against light itself. Fast forward to 1915, when Einstein reshaped our understanding of gravity with his theory of general relativity. His equations described space and time as a flexible fabric, warped by mass and energy, but even Einstein hesitated to embrace the full implications. When German physicist Karl Schwarzschild solved these equations a year later, he uncovered something startling, a point where curvature became infinite, a mathematical boundary where time stopped. Einstein dismissed it as a quirk of numbers too bizarre to exist in nature, yet there it was, the first precise description of what we now call the event horizon. The real turning point came decades later when Robert Oppenheimer, yes, the father of the atomic bomb, took the idea further. In 1939, he and his student Hartland Snyder calculated how a massive star could collapse under its own weight, vanishing from the observable universe. Their work painted a haunting picture, a star crushing itself out of existence, leaving only a gravitational fingerprint behind. But with World War II looming, the world's attention shifted, and black holes faded into obscurity once more. What's fascinating is how close these pioneers came, armed with nothing but pen, paper, and sheer imagination. They had no X-ray telescopes, no computer simulations, just the courage to follow the math wherever it led. And the math kept whispering the same terrifying truth. Somewhere out there, the universe was hiding monsters. It would take another 30 years before technology caught up to theory, and the hunt for real black holes could begin in earnest. In 1964, astronomers stumbled upon a cosmic enigma that would change everything. Nestled in the constellation Cygnus, a faint but persistent X-ray source flickered across their detectors. They named it Cygnus X-1, and at first no one knew what to make of it. This wasn't just another star or distant galaxy. It was something far stranger, screaming its existence across the universe in bursts of high-energy radiation. Here's why this discovery sent shockwaves through the scientific community. X-rays don't usually come from empty patches of space. They're produced under extreme conditions, violent collisions, scorching heat, or matter being ripped apart. And Cygnus X-1 wasn't just emitting X-rays, it was doing so with a rhythm that defied explanation. The only plausible culprit, a black hole locked in a deadly dance with a nearby supergiant star. Picture this cosmic tango. The supergiant, weighing 20 times more than our Sun, pours its gas into the abyss. As the material spirals inward, it heats up to millions of degrees, glowing fiercely in X-rays before vanishing forever. That's the signature astronomers detected, a telltale scream of matter meeting its doom. But proving it was a black hole required piecing together an even more astonishing puzzle. The breakthrough came when scientists noticed the supergiant star wobbling, as if tugged by an invisible companion. By calculating its orbit, they deduced the unseen object's mass, roughly 15 times that of our Sun, crammed into a space smaller than a city. No known star could be that dense. Neutron stars, the universe's next most compact objects, max out at about 3 solar masses. The math left only one terrifying possibility: a black hole lurking in the shadows, revealed not by light but by its gravitational grip. What's incredible is how close we came to missing it. Without X-ray astronomy, a field still in its infancy in the 60s, Cygnus X-1 might have remained a silent mystery. Even then, skepticism lingered for years. The great physicist Stephen Hawking famously bet against its existence in 1975, joking that he'd lose only if black holes were real. By 1990, when the evidence became undeniable, he conceded defeat with good humor and a hint of awe at the universe's audacity. This discovery didn't just add a new object to astronomy's catalogue. It shattered our cosmic worldview, proving that black holes weren't just theoretical oddities but active, hungry beasts hiding in plain sight. And Cygnus X-1 was the first clue, a faint X-ray whisper that led us to the edge of the abyss. The year 1971 marked the moment when theory collided with reality, when Cygnus X-1 transformed from a curious blip on an X-ray detector into a revolution in our understanding of the cosmos. The key to cracking this cosmic code wasn't found in the X-rays alone, but in the delicate dance of a star 20,000 light-years away. astronomers trained their telescopes on a blue supergiant star named HD 22686, and what they saw sent chills down their spines. This massive star, glowing with the intensity of 500,000 suns, was wobbling through space as if tugged by an invisible leash. Here's why that wobble was so electrifying. By tracking the star's motion, scientists could calculate the mass and orbit of its mysterious companion. The numbers defied belief: an object 15 times heavier than our Sun, crammed into a space so small it would fit within the limits of a major city. No ordinary star could be that dense. Neutron stars, the densest known objects at the time, simply couldn't reach such extreme masses without collapsing. That left only one spine-tingling explanation. The X-rays pouring from this system were the death cries of gas being ripped from the supergiant and hurled into an unseen black hole's event horizon. But science demands more than just a hunch. To confirm Cygnus X-1's true nature, researchers needed a smoking gun, a signature only a black hole could leave. They found it in the X-rays themselves. As matter spirals toward a black hole, it doesn't just vanish quietly. It forms a searing hot disk, spinning at nearly the speed of light and glowing with X-rays so intense they pierce through cosmic dust like a beacon. The flickering pattern of these X-rays matched exactly what physicists predicted for a black hole's feast: erratic bursts as chunks of stellar material plummeted past the point of no return. Perhaps the most astonishing part of this discovery was how it redefined the possible. For centuries, black holes existed only as mathematical ghosts, solutions to equations too strange to be real. Yet here was Cygnus X-1, a cosmic predator caught in the act, its existence written in the tortured light of a dying star. Even the most skeptical minds had to confront the evidence. Stephen Hawking, who'd famously bet against black holes being real, later admitted that the data left no room for doubt. He paid his lost bet with a playful flourish, a year's subscription to a scandal magazine for his rival, but the gesture couldn't mask the awe beneath it. Science had just peered into the abyss, and the abyss had peered back. This breakthrough didn't just add another object to astronomy's catalogue. It flung open a door to a universe far wilder than anyone had imagined, one where space and time could twist into knots, where stars could vanish from the visible cosmos, leaving behind nothing but gravity's shadow. And all of it started with a single, flickering X-ray in the constellation Cygnus, a faint signal that whispered, "Look closer, the universe is stranger than you dreamed." Stephen Hawking wasn't just a physicist, he was a master of intellectual mischief, a scientist who thrived on bold bets and playful challenges. So when the debate over Cygnus X-1's true nature reached its peak, he couldn't resist turning it into a high-stakes wager. In 1975, he famously shook hands with fellow physicist Kip Thorne, betting a subscription to Penthouse magazine that Cygnus X-1 wasn't a black hole. On the surface, it was a cheeky gesture, but beneath it lay a deeper truth. Even Hawking, whose own work had reshaped our understanding of black holes, needed irrefutable proof before he'd believe such cosmic monsters existed. The irony is delicious. Hawking spent years unraveling the paradoxes of black holes, proving they could emit radiation now named Hawking radiation and slowly evaporate. Yet here he was, betting against their very detection. Why? Because science demands more than elegant equations. It requires evidence, the kind that leaves no room for doubt. And in the 70s, Cygnus X-1's identity still hung in a grey area. Hawking later admitted he hedged his bet partly as insurance. If black holes didn't exist, his life's work would need reinventing. The wager became a safety net disguised as skepticism, but the universe had other plans. Over the next 15 years, observations piled up. The star's wobble, the X-ray signatures, the sheer mass of the invisible object, every clue pointed to one conclusion. By 1990, even Hawking couldn't ignore the verdict. During a press conference in Kyoto, he theatrically conceded, handing Thorne an actual issue of Penthouse with a wink. The moment was light-hearted, but its significance wasn't lost on anyone. The man who'd revolutionized black hole physics had just publicly acknowledged their existence in the wild, thanks to a discovery he'd once playfully doubted. What makes this story so compelling isn't just the science, it's the humanity behind it. Hawking's bet wasn't about ego, it was about the joy of scientific inquiry, the thrill of testing ideas against reality. His concession wasn't defeat, it was celebration. In a single, humorous gesture, he reminded the world that even the greatest minds must bow to evidence, and that doubt isn't the enemy of discovery but its essential partner. After all, if a theorist as brilliant as Hawking could question his own predictions, perhaps we should all embrace uncertainty as the price of unraveling the universe's deepest mysteries. Cygnus X-1 isn't just any black hole, it's a cosmic heavyweight with a voracious appetite, tipping the scales at 15 times the mass of our Sun. This colossal object packs more raw gravitational power than most stars could ever dream of. To put that into perspective, if you could somehow swap our Sun for Cygnus X-1, its gravity would instantly shred every planet in the solar system like tissue paper. But here's the twist: despite its staggering mass, the black hole itself is eerily compact. All that matter is crushed into a space no wider than Manhattan, creating a gravitational pull so intense that even light gets dragged kicking and screaming into the void. 6,000 light-years away, nestled in the constellation Cygnus, this monster isn't dining alone. It's locked in a deadly embrace with a blue supergiant star, a celestial partner 20 times heavier than our Sun. Imagine a cosmic vampire slowly draining the life from its companion. Every second, massive streams of superheated gas spiral off the star, funneled into the black hole's clutches by gravity's unrelenting grip. But this isn't a clean process. As the stolen matter plummets toward oblivion, it doesn't just vanish quietly. Instead, it forms a seething, glowing maelstrom called an accretion disk, a whirlpool of plasma hotter than the core of a nuclear explosion. The physics here is mind-bending. Gas in the disk doesn't fall straight in. It spirals at nearly the speed of light, friction heating it to millions of degrees. At these temperatures, the material doesn't just glow. It screams in X-rays, broadcasting its demise across the galaxy. That's how we first detected Cygnus X-1, not by seeing the black hole itself, but by catching the death throes of its last meals. The disk's inner edge marks the event horizon, the point where even X-rays can't escape. Beyond that, the laws of physics as we know them simply stop. What's truly astonishing is how this system balances on a knife's edge. The supergiant star isn't just passively donating gas, it's fighting back with ferocious stellar winds trying to hold onto its material. The black hole, in turn, shapes those winds into a chaotic dance, creating shock waves and turbulence that astronomers can detect from Earth. It's a cosmic tug of war where both players are reshaping each other in real time. And in a few million years, the star will lose. Either it'll be completely devoured or it'll explode as a supernova, potentially kicking the black hole across the galaxy like an interstellar billiard ball. This isn't just a spectacle, it's a laboratory. Cygnus X-1 gives us a front-row seat to extreme physics we could never replicate on Earth. The accretion disk alone defies intuition. Magnetic fields twisted into knots, jets of particles shoot out at near light speed, and time itself slows to a crawl near the event horizon. Every flicker of X-rays carries clues about how matter behaves under conditions so brutal they warp the fabric of reality. And yet, for all its fury, Cygnus X-1 is just one of millions, maybe billions of black holes lurking in our galaxy. The eerie part, we're seeing this system as it was 6,000 years ago, when human civilizations were just beginning to record history. By now, the star may have already met its fate. But its light, its final screams are still reaching us, a delayed broadcast from a cosmic drama unfolding at a glacial pace. That's the paradox of studying deep space. Even as we uncover the secrets of black holes, we're always peering into the past, watching shadows of events that unfolded long before we existed. Cygnus X-1 isn't just a scientific curiosity, it's a time capsule, a reminder that the universe operates on scales both unimaginably vast and infinitesimally small. Picture the final moments of a star's stolen gas as it plunges toward a black hole's event horizon. This isn't a quiet surrender, it's a violent, high-energy spectacle. As material spirals inward, it doesn't fall straight down like a rock into a well. Instead, it gets caught in a chaotic whirlpool called an accretion disk, where friction and gravity team up to create some of the most extreme conditions in the universe. Temperatures here soar to millions of degrees, hot enough to strip atoms bare and send them screaming across the electromagnetic spectrum as X-rays. That's the eerie glow we detect from Earth, the death rattle of matter being torn apart atom by atom. But the drama doesn't stop there. Some black holes, like Cygnus X-1, take this cosmic carnage to the next level by shooting out jets of particles at nearly the speed of light. These aren't just random bursts, they're precision engineered by physics, launched straight from the poles of the black hole like interstellar fire hoses. How does a black hole, famous for sucking everything in, manage to blast matter outward? The secret lies in the accretion disk's magnetic fields, which get twisted into cosmic tornadoes by the disk's insane rotation. Some particles get caught in these magnetic whirlwinds and slingshotted away before they ever reach the event horizon, escaping in narrow beams that can stretch for thousands of light years. These jets are so powerful they can outshine entire galaxies, visible across the universe. When they plow into surrounding gas clouds, they create shockwaves that spark new star formation, a bizarre case of destruction birthing creation. It's like a celestial demolition crew accidentally planting forests in the wreckage. And here's the wildest part. We're seeing this play out in real time with telescopes like Chandra and Hubble. The same forces that devour stars also sculpt the cosmos on a colossal scale, proving that even the universe's most destructive monsters can be accidental artists. What's humbling is realizing we're only catching fragments of the show. From our vantage point, the accretion disk's inner edge, where gravity redraws the rules of physics, is forever hidden behind the event horizon's veil. We see the X-rays, the jets, the stellar material screaming its last, but the black hole's darkest secrets remain locked away. Yet every flicker of light, every twist in those relativistic jets is a cipher waiting to be decoded, a clue to how the universe handles energy and matter under conditions we can scarcely imagine. Studying a black hole is like trying to solve a murder mystery where the culprit leaves no fingerprints, no DNA, and vanishes without a trace. By their very nature, black holes are the ultimate cosmic stealth operatives, invisible by definition because not even light can escape their grasp. So how do astronomers detect something that emits no light, reflects no signal, and hides behind an impenetrable veil of darkness? The answer lies in reading the crime scene, the twisted space around them, the terrified screams of matter being ripped apart, and the subtle gravitational fingerprints they leave on the cosmos. One of the most telling clues comes from their effect on nearby stars. Imagine a star moving through space as if it's dancing alone. Then suddenly, its path starts to wobble unpredictably, as if tugged by an unseen partner. That's exactly what happened with Cygnus X-1's companion star. By tracking these gravitational disturbances, scientists can calculate the mass and orbit of the hidden object, even if they never see it directly. It's like deducing the presence of an invisible planet by watching its stars shimmy back and forth. But stars aren't the only victims giving black holes away. Gas and dust unfortunate enough to wander too close get stretched into a swirling disk of superheated plasma, glowing fiercely with X-rays before vanishing forever. This accretion disk acts like a cosmic neon sign, broadcasting the black hole's location across the universe. The hotter and faster the material spins, sometimes reaching speeds close to light itself, the brighter the X-ray flare. Telescopes like Chandra and New Star specialize in catching these high-energy death cries, turning them into detailed maps of the chaos around the event horizon. Then there's the subtle art of gravitational lensing, where a black hole's immense gravity bends passing light like a funhouse mirror. If a distant star's light happens to travel near a black hole, its path warps, creating distorted or multiple images of the same star. This effect isn't just a parlor trick. It allows scientists to measure the black hole's mass and even test Einstein's predictions about how space-time bends under extreme conditions. But perhaps the most jaw-dropping tool in the detective kit arrived in 2019, when the Event Horizon Telescope collaboration unveiled the first ever image of a black hole's shadow. Using a global network of radio telescopes acting as one Earth-sized instrument, they captured the eerie silhouette of M87's supermassive black hole, outlined by the fiery glow of its accretion disk. This wasn't a direct photo. No telescope can peer past the event horizon, but a painstaking reconstruction of radio waves bent by the black hole's gravity. The image confirmed what equations had predicted for decades: a dark void encircled by a lopsided ring of light, where space-time itself swirls like water down a drain. What's fascinating is how each method fills in a different piece of the puzzle. X-rays reveal the violence of matter in its death throes. Star motions expose the silent tug of gravity. Lensing bends the very fabric of reality to betray a hidden mass. And now, radio wave snapshots give us a ghostly portrait of the abyss itself. Together, they prove that even the universe's most secretive objects can't hide forever. Not when science knows how to listen to their whispers, read their distortions, and piece together the story they're desperate to conceal. For centuries, black holes existed only as mathematical phantoms, dark stars predicted by theory but never seen. Even after Cygnus X-1 proved their existence in the 1970s, they remained frustratingly invisible, their secrets locked behind event horizons no telescope could breach. That all changed on April 10, 2019, when humanity peeled back the cosmic curtain for the first time. The Event Horizon Telescope collaboration released an image that made history: a fiery ring of light surrounding the pitch-black shadow of the supermassive black hole at the heart of galaxy M87, 55 million light-years away. This wasn't just a photograph, it was a triumph of ingenuity on an almost unimaginable scale. Picture this: 8 radio telescopes scattered across the globe from Hawaii to the South Pole, synchronized to act as one Earth-sized instrument. Together, they captured radio waves emitted by superheated gas swirling around M87's black hole, then spent 2 years stitching that data into a single, ghostly portrait. The result: a lopsided golden halo framing a dark void, a cosmic bullseye where space-time itself vanishes into the abyss. What makes this image so revolutionary isn't just its beauty, but what it confirmed. Einstein's equations had predicted such a shadow for a century, yet seeing it in reality was like catching a unicorn on camera. The asymmetry of the ring, brighter on one side, proved the black hole was spinning, dragging space-time around it like a whirlpool. The size of the shadow matched predictions almost perfectly, giving physicists confidence that general relativity still holds true even in gravity's most extreme arena. Compare this to how we studied Cygnus X-1 decades earlier. Back then, astronomers were detectives piecing together circumstantial evidence: X-ray flickers, a wobbling star, gravitational nudges. It was like hearing a monster's growls from behind a locked door. M87's image was the moment we finally kicked that door open, revealing the beast itself. Yet both discoveries share a deeper kinship. Each relied on pushing technology beyond its limits. Just as X-ray astronomy had to mature before Cygnus X-1 could be understood, the Event Horizon Telescope required advances in atomic clocks, supercomputing, and global coordination that would have been unthinkable in the 1970s. The real magic lies in how these milestones complement each other. Cygnus X-1 showed us black holes could be small, stellar-scale predators lurking in our galactic backyard. M87 revealed their supermassive cousins, behemoths billions of times heavier, anchoring entire galaxies. One taught us black holes exist, the other showed us their face. Together, they prove science isn't just about eureka moments, but about building a ladder of understanding, rung by rung, until we can reach the stars. And this is only the beginning. The Event Horizon Telescope has since turned its gaze toward Sagittarius, a star, the quieter black hole at the Milky Way's heart. Future upgrades could capture sharper images, even movies of accretion disks in motion. Imagine watching a black hole's shadow ripple as it devours a star, or tracing magnetic fields as they launch jets of plasma into the cosmos. We're no longer just hunting shadows, we're learning to read the universe's darkest ink, one photon at a time. Black holes come in more flavors than you might expect, each with its own origin story, size, and cosmic role. Let's start with the smallest but no less terrifying category, stellar mass black holes like Cygnus X-1. These form when massive stars, at least 20 times heavier than our Sun, exhaust their nuclear fuel and collapse under their own gravity. The end isn't quiet. The star's core implodes in a cataclysmic supernova explosion, while what's left behind crumples into a singularity so dense it punctures the fabric of space-time. These black holes typically weigh between 5 and 50 solar masses, small enough to orbit stars yet powerful enough to tear them apart. Then there are the universe's true monsters, supermassive black holes. These lurk at the centers of galaxies, including our own Milky Way, tipping the scales at millions or even billions of solar masses. Unlike their stellar mass cousins, their origins remain one of astronomy's grand puzzles. Did they grow from smaller black holes merging over eons, or did they form directly from collapsing gas clouds in the early universe? However they arose, their influence is staggering. A supermassive black hole's gravity can shape entire galaxies, dictating the motion of stars thousands of light years away. The one at our galaxy's core, Sagittarius, a star, is relatively quiet. But in other galaxies, these behemoths power quasars, the brightest objects in the universe, by devouring stars and gas at breakneck speeds. Between these extremes lies a mysterious middle child, intermediate mass black holes. Weighing in at hundreds to thousands of solar masses, they've been far harder to detect. Some might form from the collisions of stellar mass black holes in dense star clusters, while others could be the ancient seeds from which supermassive black holes grew. In 2020, astronomers spotted tantalizing evidence of one in the outskirts of the Andromeda Galaxy, revealed by the way it shredded a wandering star. These elusive objects could be the missing link in our understanding of how black holes evolve across cosmic time. What's fascinating is how each type leaves its own fingerprint on the cosmos. Stellar mass black holes like Cygnus X-1 are the scattered remnants of dead stars, lurking invisibly until they snare a passing cloud or star. Supermassive black holes act as galactic anchors, their gravity shaping the very structure of the universe around them. And intermediate mass black holes, they might hold clues to how the first black holes formed, bridging the gap between the tiny and the titanic. Together, they remind us that the universe thrives on variety, even in its darkest, most destructive corners. The death of a massive star isn't just an ending, it's a cosmic metamorphosis, a violent rebirth into something stranger and darker. Picture a star 20 times heavier than our Sun, burning through its nuclear fuel at a furious pace. For millions of years, it's a titanic fusion reactor, crushing hydrogen into helium, then helium into carbon, forging heavier elements in its core like a celestial blacksmith. But this forging has an expiration date. Eventually, the star runs out of fuel to burn, and that's when gravity, the silent force it's been fighting its entire life, finally wins the war. The collapse begins in the star's core, now packed with iron. Unlike lighter elements, iron doesn't release energy when fused, it absorbs it. With no outward pressure left to resist gravity's pull, the core implodes in less than a second. Atoms are crushed together so violently that protons and electrons merge into neutrons, releasing a flood of neutrinos, ghostly particles that streak outward at nearly the speed of light. The outer layers of the star, suddenly without support, come crashing down like a collapsing skyscraper, then rebound off the ultra-dense core in a shockwave of unimaginable power. This is the supernova, a detonation so bright it can outshine an entire galaxy for weeks, scattering newly forged elements across space like cosmic shrapnel. What's left behind depends on the star's original mass. For smaller stars, the core becomes a neutron star, a city-sized orb so dense a teaspoon of it would weigh 1 billion tons on Earth. But for the most massive stars, even neutron stars aren't the end game. If the collapsing core weighs more than about 3 solar masses, no known force can stop its downward spiral. Neutrons themselves crumble under the strain, and the core collapses into a singularity, a point of infinite density where space and time curve so sharply that the laws of physics as we know them cease to apply. A black hole is born. This is likely how Cygnus X-1 came into existence. Before it was a black hole, it was a colossal star, perhaps 40 times the mass of our Sun, that lived fast and died young. Its supernova would have been a spectacle visible across the galaxy, a flash of light announcing the birth of something far more enigmatic. The explosion would have kicked the newborn black hole across space, but not too far today. It's still gravitationally bound to its massive blue companion star, a relic of the binary system that existed before the cataclysm. What's astonishing is how much this process shapes the universe. That supernova didn't just create a black hole, it seeded space with heavy elements, oxygen, carbon, gold, that would someday form planets, oceans, even life. The very iron in your blood was forged in the heart of a dying star like Cygnus X-1's progenitor, and the black hole itself, it's now a gravitational anchor, warping space around it, bending light, and dragging time to a near standstill at its event horizon. The death of one star became the birth of a cosmic phenomenon that still challenges our understanding of reality today. Einstein's theory of relativity revealed a truth far stranger than fiction. Gravity doesn't just bend space, it twists time itself. Nowhere is this more extreme than near a black hole like Cygnus X-1, where the gravitational pull is so intense that time slows to a crawl. Picture an astronaut orbiting just outside the event horizon, their clock ticking at a fraction of the speed of someone watching from a safe distance. For every hour they experience, years might pass elsewhere in the universe. It's not science fiction, it's the unavoidable consequence of gravity warping the very fabric of reality. To grasp why this happens, think of space-time as a stretchy trampoline. A black hole is like a bowling ball so heavy it creates a bottomless pit in the fabric. The closer you get to that pit, the more stretched the trampoline becomes, and just as the fabric distorts, so does time. Light struggling to climb out of that gravitational well loses energy, its wavelength stretching into redder, slower frequencies. This effect, called gravitational redshift, is nature's way of signaling that time itself is running slower near the black hole's edge. Now apply this to Cygnus X-1. If you could hover near its event horizon, surviving the tidal forces that would otherwise rip you apart, you'd witness time behaving in ways that defy intuition. A single orbit around the black hole might take mere minutes from your perspective, but to an observer on Earth, that same journey could span decades. The difference isn't an illusion, it's a fundamental rift in how time flows. GPS satellites orbiting Earth actually account for a milder version of this effect, adjusting their clocks because time ticks slightly faster in weaker gravity. Near Cygnus X-1, the effect is so extreme it borders on the surreal. Here's where it gets even weirder. If you could peer outward from your precarious perch near the event horizon, the entire universe would appear to speed up. Distant stars would streak across the sky like comets, their light blue shifted into higher energies as if someone hit the fast-forward button on reality. Meanwhile, anyone observing you would see your movements slow to a near standstill, your image frozen in time as the black hole's gravity stretches the light you emit into an infinite redshift. This time warping isn't just a theoretical quirk, it has real observational consequences. Cygnus X-1's accretion disk, that swirling vortex of doomed matter, emits X-rays that carry subtle fingerprints of time dilation. As gas spirals inward, its light takes longer to escape the deepening gravity well, stretching the intervals between detectable X-ray pulses. Astronomers can measure this delay, effectively using the black hole as a cosmic laboratory to test relativity under conditions impossible to recreate on Earth. What's humbling is realizing that all of this, time-bending, light-stretching, reality itself unraveling, was encoded in Einstein's equations over a century ago. He never lived to see black holes confirmed, yet his math predicted their behavior with eerie precision. Cygnus X-1, once a mere speck of X-ray light, now stands as one of relativity's most compelling validations. It's a reminder that the universe doesn't just operate by rules we can see sometimes. The deepest truths hide in the warped silence of a black hole's shadow. Approaching Cygnus X-1 wouldn't just be dangerous, it would be a surreal, slow-motion nightmare where the laws of physics turn against you. This phenomenon, whimsically called spaghettification, is no exaggeration. Imagine dangling your feet toward the black hole's event horizon. At first, nothing seems unusual, but as you drift closer, an invisible force tugs at your toes harder than your head, stretching you longer and thinner like cosmic taffy. The difference in gravity between your head and feet, just a few meters apart, becomes so extreme that your body can't hold itself together. Bones snap, muscles fray, and within seconds, you're not a person anymore but a stream of atoms being pulled into a gravitational vortex. The science behind this is as precise as it is horrifying. Tidal forces, the same ones that make Earth's oceans bulge toward the moon, become lethal near a black hole. Cygnus X-1's immense gravity creates a gradient so steep that even light can't escape its clutches. For an object like a star or spacecraft, the effect is grotesquely predictable. The side facing the black hole feels exponentially stronger gravity than the side pointing away, stretching everything into a narrow filament. Long before crossing the event horizon, matter isn't just torn apart, it's unraveled atom by atom, a process scientists poetically call nuclear poster in neutron stars, where particles get crushed into spaghetti like strands. But here's the twist, not all black holes spaghettify you the same way. Smaller black holes like Cygnus X-1 are far more vicious than their supermassive cousins. Their event horizons are smaller, so the tidal forces ramp up dramatically over shorter distances. Falling into one would shred you before you even realized what was happening. By contrast, a supermassive black hole's event horizon is so vast that you could theoretically cross it unscathed, at least until the singularities' gravity inevitably crushed you. This isn't just morbid speculation. In 2019, astronomers witnessed a star suffering this fate in real time. A black hole in a galaxy 215 million light-years away ripped apart a sun-like star, stretching its gas into a luminous strand before devouring it. The event, dubbed the tidal disruption flare, was a chilling confirmation of what theorists had long predicted. Black holes don't just swallow, they play with their food first. For Cygnus X-1, the process would be even more extreme. Its 15 solar mass frame generates tidal forces capable of shredding stars from millions of kilometers away. The accretion disk we see, that's the aftermath of the black hole's last meal, a swirling graveyard of matter stretched so thin it glows with the heat of 1,000 suns. And yet, amid this destruction, there's eerie beauty. The same forces that annihilate also create scattering heavy elements forged in stellar deaths, seeding future stars and planets with the building blocks of new worlds. Spaghettification isn't just a cosmic horror story. It's a reminder that gravity, the gentle force that keeps your feet on the ground, can become an unstoppable sculptor under the right conditions, twisting, stretching, and reshaping reality itself with effortless brutality. And somewhere in Cygnus, 6,000 light-years away, that same force is still at work, turning stardust into strands of luminous ruin. Long before scientists confirmed their existence, black holes already captivated our collective imagination, and few cosmic objects have left as big a mark on pop culture as Cygnus X-1. In 1977, the progressive rock band Rush immortalized it with their groundbreaking album A Farewell to Kings, featuring the epic track Cygnus X-1. The song wasn't just a sci-fi fantasy. It wove the black hole's mystery into a sonic journey, blending science with mythology. Guitarist Alex Lifeson even crafted the song's dissonant chords to mimic the eerie, warped reality near the event horizon. It was art drawing straight from the cosmos, proving that even in the 70s, black holes weren't just laboratory curiosities. They were muses Hollywood couldn't resist either. Take Interstellar, where Matthew McConaughey's character plunges into Gargantua, a supermassive black hole rendered with jaw-dropping accuracy. Physicist Kip Thorne, the same scientist who once bet against Cygnus X-1, worked closely with the filmmakers to ensure the black hole's depiction followed real relativistic equations. The result, a spinning, glowing accretion disk distorted by gravitational lensing, so precise it spawned legitimate scientific papers. But here's the kicker: without Cygnus X-1's discovery decades earlier, Interstellar's black hole might have looked like a cartoon void. Real science gave the fiction its haunting realism. Then there's Event Horizon, a cult horror film that took the nightmarish side of black holes literally. While the movie played fast and loose with physics, its core idea, a ship disappearing into a black hole and returning with something wrong, tapped into our primal fear of the unknown. Even Treasure Planet, Disney's animated space adventure, featured a black hole as both obstacle and gateway, mirroring humanity's dual view of these cosmic phenomena, terrifying yet brimming with possibility. Video games have gotten in on the action too. Destiny 2's The Witch Queen expansion introduced a black hole weapon called Black Hole Generator, while Elite Dangerous lets players fly perilously close to Sagittarius, a star's event horizon. These virtual encounters might not be textbook accurate, but they spark curiosity, turning players into armchair astrophysicists. What's fascinating is how Cygnus X-1's legacy bridges hard science and wild creativity. It's proof that discovery doesn't just live in journals. It fuels stories, songs, and screens, reminding us that the universe's most enigmatic phenomena are also its most inspiring. Whether through music that bends genres like space-time or films that make relativity visceral, black holes have become more than astronomical oddities. They're cultural touchstones, reflecting our endless drive to explore the unknown, even when the unknown might spaghettify us. One of the biggest myths about black holes is that they're cosmic vacuum cleaners, endlessly sucking up everything in their path. If that were true, Cygnus X-1 would have devoured its companion star long ago. Yet 6,000 light-years away, this binary system still thrives. The reality is far more nuanced. Black holes don't indiscriminately hoover up matter. They obey the same gravitational rules as any other massive object. Their pull is only unstoppable if you venture too close, crossing the event horizon. Outside that boundary, orbits are possible just like Earth, circling the Sun without falling into it. In fact, if our Sun magically became a black hole of equal mass tomorrow, Earth's orbit wouldn't change. The grip of gravity depends on mass, not whether an object is lightless or not. Another persistent misconception is that black holes are rare, lurking only in distant corners of the universe. Cygnus X-1 proves otherwise. It's right in our galactic neighborhood. Astronomers now estimate there could be over 100 million stellar mass black holes in the Milky Way alone, remnants of massive stars that died in supernova. Some might even drift closer than Proxima Centauri, invisible unless they tug on nearby stars or gas. And let's not forget supermassive black holes, which sit at the heart of nearly every large galaxy. Far from exotic anomalies, black holes are a fundamental part of cosmic architecture. Then there's the sci-fi trope that black holes are portals to other dimensions or time machines. While Einstein's equations do allow for hypothetical wormholes, bridges through space-time, there's zero evidence Cygnus X-1 or any known black hole fits this description. Crossing the event horizon isn't a gateway, it's a one-way trip to being crushed into quantum spaghetti. Even Hawking radiation, the slow leak of energy from black holes, happens over timescales trillions of times longer than the current age of the universe. No human or alien is surfing through one anytime soon. Perhaps the most ironic myth is that black holes are empty. Cygnus X-1's accretion disk reveals the opposite, a churning maelstrom of superheated matter, magnetic fields, and energy. That glowing disk isn't just a side effect, it's a powerhouse. Some black holes convert more mass into energy than 1 million nuclear reactors, making them the universe's most efficient engines. Far from being voids, they're dynamic, chaotic, and strangely creative. The heavy elements forged in their stellar deaths become the building blocks of new stars, planets, and even life. The truth is, black holes don't need exaggerations to be fascinating. Their real physics, time dilation, spaghettification, gravitational waves, is bizarre enough without inventing cosmic vacuum cleaners or interstellar shortcuts. Cygnus X-1, with its X-ray screams and relentless hunger, reminds us that reality often outshines fiction. The universe's darkest marvels aren't just destructive, they're sculptors, shaping galaxies and testing the very laws that hold existence together. And that's more thrilling than any myth. Black holes aren't just gravitational monsters, they're quantum puzzles wrapped in cosmic enigmas. At the intersection of Einstein's relativity and quantum mechanics, these dark giants force us to confront questions that challenge the very foundations of physics. Take Hawking radiation, the brilliant insight Stephen Hawking unveiled in 1974. Imagine the vacuum of space near a black hole's event horizon, where quantum fluctuations constantly create pairs of virtual particles. Normally, these particles annihilate each other instantly, but if one falls into the black hole while the other escapes, the black hole loses mass over time, slowly evaporating. This isn't science fiction, it's a real process, one that means even black holes aren't eternal. Hawking's discovery turned the cosmos upside down. If black holes can evaporate, what happens to all the information they've swallowed? According to quantum mechanics, information, the fundamental properties of particles, can never be destroyed. Yet black holes seem to erase it completely, vanishing matter into a singularity where even the universe's rules break down. This contradiction, known as the information paradox, has sparked decades of debate. Some physicists argue the information leaks out via Hawking radiation, scrambled beyond recognition. Others propose it's preserved in a holographic imprint on the event horizon, like a cosmic DVD encoding everything that fell in. The stakes couldn't be higher. If information truly vanishes, quantum mechanics, the framework underlying everything from atoms to smartphones, needs rewriting. That's why labs worldwide are racing to simulate black hole physics using quantum computers and ultra-cold atoms. In 2020, scientists even created a holographic black hole in a lab, using entangled photons to mimic information scrambling at the event horizon. These experiments don't just test Hawking's ideas, they push the boundaries of how we understand reality itself. What's poetic is how Cygnus X-1, the first black hole we confirmed, now plays a role in this quantum drama. Its X-ray emissions carry faint hints of quantum effects near the event horizon, subtle fingerprints that telescopes like JWST and next-generation detectors aim to decode. Every flicker of light from its accretion disk might hold clues about how information resists annihilation, or how space-time itself fractures under extreme conditions. This isn't just theoretical noodling. Unraveling these mysteries could redefine our understanding of the universe's fate. If black holes evaporate, will the cosmos end in a whisper of Hawking radiation? Or is information eternally preserved, waiting to be decoded in some far future universe? Cygnus X-1, once a mere curiosity, now sits at the heart of these questions, a reminder that the darkest objects in the sky might illuminate the deepest truths. The discovery of Cygnus X-1 didn't just open our eyes to black holes, it unveiled a new way of seeing the universe itself. Today, astronomers don't rely on a single type of data to decode cosmic mysteries. They combine X-rays, radio waves, and even ripples in space-time called gravitational waves. This multi-messenger approach transforms how we study black holes, turning them from invisible specters into multidimensional puzzles we can piece together. Take X-rays, the same signals that first betrayed Cygnus X-1's presence. They're still crucial, revealing the violent dance of matter heating up as it spirals into a black hole's accretion disk. But now, we layer on radio telescopes which catch the high-speed jets shooting from the black hole's poles, beams of particles so energetic they can travel millions of light years. Together, these two perspectives paint a fuller picture. The X-rays show us the feast, while the radio waves reveal the leftovers being hurled back into space. Then there's the game-changer, gravitational waves. When two black holes collide, they send shockwaves through the fabric of space-time itself, disturbances so subtle that detectors like LIGO had to measure shifts smaller than an atom's width to catch them. In 2015, LIGO made history by detecting these waves from a black hole merger over 1 billion light-years away. Suddenly, we weren't just observing black holes indirectly through their effects on light. We were hearing them through the vibrations they imprint on the universe. Now imagine combining all three. Picture a scenario where a black hole merger triggers gravitational waves, while its aftermath lights up in X-rays and radio flares. That's multi-messenger astronomy in action, a cosmic detective story where every clue matters. In 2017, we got a taste of this when LIGO spotted two neutron stars colliding. Telescopes worldwide swiveled to catch the aftermath in every wavelength, from gamma rays to radio waves, confirming theories about how such crashes forge heavy elements like gold and platinum. What's thrilling is how Cygnus X-1 laid the groundwork for this revolution. Its X-ray emissions taught us where to look, its radio jets hinted at the energy black holes eject, and now gravitational waves reveal their collisions. Each messenger fills in gaps the others leave behind. X-rays show us the heat of destruction, radio waves map the aftermath, and gravitational waves expose the moment of impact. This isn't just about collecting more data, it's about seeing the universe in stereo. Just as your brain combines sight, sound, and touch to understand the world, multi-messenger astronomy merges disparate signals into a cohesive story. And the story keeps getting richer. New detectors like the upcoming LISA mission will hunt for lower frequency gravitational waves, potentially catching supermassive black holes merging at the hearts of galaxies. Meanwhile, telescopes like the James Webb Space Telescope peer deeper into the infrared, spotting black holes hidden behind cosmic dust. Cygnus X-1 was our first black hole, but it won't be our last. With every new tool, we're not just finding more of these cosmic enigmas, we're understanding them in ways that would have stunned the astronomers who first puzzled over that flickering X-ray signal in the 60s. The universe speaks in many languages: light, waves, ripples, and now at last we're learning to listen. HD 22686 isn't just any star, it's a cosmic titan locked in a lethal embrace with one of the universe's most infamous predators. This blue supergiant, 20 times more massive than our Sun and radiating 500,000 times more light, is the unsung protagonist in Cygnus X-1's story. Every second, it pours torrents of stellar wind into the black hole's clutches, a sacrificial offering that fuels the system's eerie X-ray glow. But this isn't a one-sided relationship. The black hole's gravity sculpts the star's very shape, stretching it into a teardrop as it orbits their shared center of mass. The dance between these two objects is as beautiful as it is brutal. HD 226-86 completes an orbit every 5.6 days, racing through space at speeds that would make a jetliner look stationary. As it moves, the black hole's tidal forces strip away its outer layers, pulling gas into a spiraling stream that connects the two like a celestial umbilical cord. This stolen material doesn't just vanish quietly. It forms the searing accretion disk we detect from Earth, a glowing testament to the star's slow demise. Yet the star isn't helpless. Its sheer size and ferocious stellar winds push back, creating a dynamic balance where the black hole can't devour it whole, at least not yet. The system exists in a temporary equilibrium, but time is running out for the supergiant. In a few million years, it will exhaust its nuclear fuel, leading to one of two apocalyptic outcomes. Either it will collapse directly into another black hole, creating a binary pair of gravitational monsters, or it will explode as a supernova, potentially kicking Cygnus X-1 clear across the galaxy like a cosmic bullet. What's fascinating is how this relationship mirrors the universe's cyclical nature. The material HD 226-86 loses today. Carbon, oxygen, iron will someday seed new stars and planets. Even as it's consumed, it's scattering the building blocks of future worlds, and the black hole, it's not just a destroyer. By heating and accelerating this material, it's indirectly shaping the chemistry of its galactic neighborhood. The star's fate also holds clues about black hole formation across the cosmos. Most stellar mass black holes likely form in binary systems like this one, where one star collapses and begins feeding on its partner. By studying HD 226-86's wobbles, its composition, and the rate it's being stripped bare, astronomers can reconstruct the life cycles of countless similar pairings hidden throughout the Milky Way. Right now, 6,000 light-years away, this cosmic drama unfolds in slow motion, a reminder that even the universe's most violent processes are patient, unfolding over timescales dwarfing human history. But every flicker of X-rays from Cygnus X-1 is a snapshot of that inevitable end, a star's final act written in light and gravity. The hunt to unravel black holes isn't slowing down. It's accelerating with tools so advanced they'd seem like science fiction to the astronomers who first detected Cygnus X-1. Leading the charge is LISA, the Laser Interferometer Space Antenna, a revolutionary mission set to launch in the 2030s. Unlike ground-based detectors like LIGO, which catch the high-frequency gravitational waves from merging stellar mass black holes, LISA will float in space as a trio of satellites spanning millions of kilometers. This sprawling network will act as a precision microphone tuned to the universe's lowest frequencies, ones emitted by supermassive black holes spiraling toward collisions over millions of years. Imagine hearing the deepest notes in the cosmos for the first time. LISA sensitivity could let us eavesdrop on black holes like Cygnus X-1 in their quieter moments, capturing the subtle ripples they create as they orbit companion stars or slurp down gas clouds. But the real prize, detecting black holes from the universe's infancy, primordial monsters that may have formed from dense patches of matter just after the Big Bang. These ancient relics, invisible to conventional telescopes, could rewrite our understanding of how black holes seed galaxies. Then there's the James Webb Space Telescope's successor, the Habitable Worlds Observatory, slated for the 2040s. While designed to hunt Earth-like planets, its advanced optics will also peer into the chaotic hearts of galaxies. spotting the faint infrared glow of black holes hidden behind cosmic dust, regions where even Cygnus X-1's X-rays can't penetrate. And don't forget the next generation of X-ray telescopes, like ESA's Advanced Telescope for High-Energy Astrophysics. With resolution 50 times sharper than current instruments, it could map the magnetic fields at Cygnus X-1's event horizon in unprecedented detail, revealing how black holes launch jets of particles at near light speed. These missions share one audacious goal: to see black holes not just as static objects, but as dynamic players in cosmic evolution. LISA might catch two supermassive black holes circling each other in a dance lasting centuries. Next-gen X-ray telescopes could film accretion disks flickering in real time, like a time-lapse of a storm on Jupiter. The data could even settle Hawking's information paradox by revealing whether black holes truly erase what they swallow or somehow preserve it in their gravitational grip. What's thrilling is how these tools build on Cygnus X-1's legacy. That first discovery taught us where to look. Now we're learning how to listen, touch, and even smell the universe, metaphorically speaking, with sensors that span the electromagnetic spectrum and beyond. The next decade won't just add to our black hole catalog, it'll transform them from cosmic curiosities into open books, their pages written in gravity, light, and space-time itself. Imagine trying to recreate the death of a star not in a lab, but inside a supercomputer. That's exactly what astrophysicists do when they simulate black hole mergers like the one that likely birthed Cygnus X-1. These aren't just fancy animations, they're mathematical maelstroms, crunching Einstein's equations with such precision they can predict how space-time ripples when two black holes collide. The Frontier supercomputer, one of the fastest in the world, dedicates millions of processor hours to these simulations, solving problems so complex they'd take a human centuries to calculate by hand. The process starts with data from real black holes' mass, spin, even the chemical composition of their accretion disks. Plugging these into relativity equations, scientists can rewind time, simulating the moment a massive star collapses or two black holes spiral toward cataclysmic merger. One groundbreaking simulation revealed how Cygnus X-1 might have formed. A supernova explosion so asymmetrical it kicked the newborn black hole across space, yet left it bound to its massive companion star. The models even show the gravitational waves such an event would generate ripples in space-time that match signals later detected by observatories like LIGO. But these simulations aren't just about replaying cosmic history. They're stress tests for Einstein's theory. When black holes merge in supercomputers, physicists look for discrepancies, places where reality might diverge from relativity's predictions. So far, Einstein's equations hold up spectacularly, even in scenarios where gravity reaches 100 billion times Earth's pull. Yet subtle anomalies in Cygnus X-1's X-ray emissions hint there might still be gaps in our understanding, tiny cracks where new physics could creep in. What's astonishing is how much detail these virtual black holes reveal. Some simulations zoom in close enough to track individual magnetic field lines twisting in the accretion disk, explaining how jets like Cygnus X-1's get launched at near light speed. Others recreate the chirp sound gravitational waves make as black holes merge, a sound so accurate when LIGO first detected it in 2015. Scientists instantly recognized it from their models. The real magic happens when simulation meets observation. By comparing Cygnus X-1's actual X-ray flickers with supercomputer predictions, researchers can reverse engineer hidden properties, like the black hole's spin rate, which clocks in at an astounding 95% of the speed of light. That spin isn't just a fun fact, it's a fossil record of how the black hole formed. A clue that it likely grew by gorging on its companion star's gas for millennia. These virtual experiments also explore wilder possibilities, like what happens if black holes aren't perfectly smooth as relativity suggests, but have quantum hair encoding information about what they've swallowed. Some simulations even test whether naked singularities, black holes without event horizons, could exist, though so far, Cygnus X-1's behavior aligns stubbornly with classical physics. The takeaway: every frame of these supercomputer movies is a dialogue between theory and reality, a chance to see if Einstein's universe holds up when pushed to its limits. And as detectors grow more sensitive and simulations more lifelike, we're not just reconstructing black hole mergers, we're writing the rulebook for how gravity operates in the most extreme corners of existence. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole, not just a stellar oddity like Cygnus X-1, but a cosmic architect shaping the destiny of billions of stars. These behemoths, weighing millions to billions of times our sun's mass, are more than just gravitational traps. They're the invisible engines driving galaxy formation itself. The contrast with stellar mass black holes couldn't be starker. While Cygnus X-1's 15 solar masses make it a local predator, supermassive black holes operate on a galactic scale, their influence stretching tens of thousands of light years. Take Sagittarius, a star, the Milky Way's central black hole. Though relatively quiet today, its 4 million solar mass presence acts like a gravitational anchor, orchestrating the orbits of stars near the galactic core. But in younger galaxies, supermassive black holes are anything but passive. As they devour gas and dust, they unleash quasars, blindingly bright jets of energy that can outshine entire galaxies. These jets, powered by the black hole's spinning magnetic fields, heat surrounding gas so intensely they shut down star formation across vast regions. It's a cosmic feedback loop. The black hole's feast regulates the galaxy's growth, preventing runaway stellar births that could tear galaxies apart. What's astonishing is how this process mirrors and dwarfs what we see in systems like Cygnus X-1. Both types of black holes have accretion disks and jets, but where Cygnus X-1's jets stretch light years, supermassive black holes launch them across millions of light years, carving voids in intergalactic gas. And while stellar mass holes form from dying stars, supermassive ones likely grew from seeds in the early universe, swallowing gas or merging with others to reach incomprehensible sizes. Yet their most profound role might be in galaxy diversity. Elliptical galaxies, smooth and star-poor, often host overt black holes whose past quasar outbursts blew away their gas. Spiral galaxies like ours, with active star-forming arms, tend to have quieter black holes, their growth balanced by gentler feeding. It's as if the black hole's appetite writes the galaxy's life story, a tale of feast and famine spanning billions of years. This cosmic symbiosis raises a haunting question. Do black holes shape galaxies, or do galaxies breed black holes? The answer seems to be both. Dark matter halos likely drew in gas to form the first galaxies, but supermassive black holes then tempered that growth, preventing stellar overcrowding. Meanwhile, mergers between galaxies funnel fresh material to their central black holes, triggering new outbursts that sculpt their futures. Cygnus X-1 might be a fascinating predator, but its supermassive cousins are the unseen weavers of the cosmic web, silent, ancient, and unimaginably powerful. Imagine waking up to news that Cygnus X-1 had mysteriously moved, not light years away, but just on the outskirts of our solar system. Suddenly, that faint X-ray flicker becomes an unignorable presence, its gravity subtly tugging at the outer planets. The ethical dilemmas this scenario unleashes are as vast as the cosmos itself. Astrophysicists aren't just studying black holes anymore. They're wrestling with questions that blur the line between scientific ambition and responsibility. What happens when humanity's reach exceeds its grasp in the realm of celestial engineering? Take the idea of manipulating black holes, a concept that sounds like sci-fi but is grounded in real theoretical physics. Some proposals suggest using microscopic black holes as power sources, harnessing their Hawking radiation for near-limitless energy. others ponder whether advanced civilizations might steer black holes to reshape galaxies. The math might check out, but the risks are staggering. One miscalculation could turn a black hole into an unstoppable chain reaction, consuming everything in its path. And who gets to make these decisions? A single nation, a corporation? The ethical quagmire deepens when you consider that black holes don't respect borders, their effects ripple across light years. Now bring Cygnus X-1 closer, not just as a hypothetical, but as a cautionary tale. At 6,000 light-years away, it's a curiosity, a tenth of that distance, and its gravity starts distorting the Oort cloud, flinging comets toward the inner solar system. Within a few hundred light-years, its X-ray emissions could sterilize nearby planets. The irony is inescapable. The same phenomenon that taught us about relativity and quantum mechanics could, under different circumstances, become an existential threat. This isn't just about astronomy, it's about recognizing that some cosmic discoveries come with Pandora's box of responsibilities. The debate touches deeper philosophical currents too. If we ever develop the technology to manipulate black holes, do we have the right to alter fundamental cosmic processes? Black holes aren't just objects, they're pivotal to galaxy formation, star birth, even the flow of time itself. Tinkering with them could rewrite the universe's evolutionary script in ways we can't predict. Indigenous cosmologies and environmental ethics alike urge caution. What looks like progress to one culture might be cosmic vandalism to another. Perhaps the most unsettling question isn't can we, but should we? In a universe where humanity is still learning its place, the power to reshape black holes feels akin to handing a toddler a detonator. The allure is undeniable. Black holes represent the ultimate frontier of control over nature. But with that control comes a weighty truth. Some forces might be best left undisturbed, not because we can't touch them, but because we're not yet wise enough to bear the consequences. The story of Cygnus X-1 isn't just about discovery. It's a mirror reflecting our own readiness to wield the universe's most formidable tools. What if Cygnus X-1 is just the tip of the cosmic iceberg, one small piece of a puzzle so vast we're only beginning to glimpse its edges? For all we've learned about black holes, the universe still guards secrets that defy even our boldest theories. Take dark matter, the invisible glue holding galaxies together. We've mapped its gravitational fingerprints across the cosmos, yet its true nature remains elusive. Could black holes be the key? Some physicists speculate that primordial black holes, tiny ones formed in the chaos of the Big Bang, might actually be dark matter hiding in plain sight. If true, every galaxy could be swimming in countless microscopic black holes, their collective gravity shaping the universe's structure. Then there's the enigma of gamma-ray bursts, mysterious explosions so powerful they outshine entire galaxies for seconds. While some come from collapsing stars, others defy explanation. One leading theory, distant black holes merging in cosmic smash-ups, ripping space-time so violently they send shockwaves across the universe. Imagine two black holes like Cygnus X-1 spiraling toward collision, warping space around them until, bang, a flash visible halfway across the cosmos. These events might be the universe's most energetic phenomena, and we're only starting to decode their language. Even black holes themselves harbor unanswered questions. What lies beyond the event horizon? Einstein's equations suggest a singularity, a point where density becomes infinite and physics breaks down. But some theories, like loop quantum gravity, propose there's no singularity at all. Instead, the collapsing matter might rebound, birthing a new universe in a process called a white hole. It's a dizzying thought. Every black hole could be a cosmic matryoshka doll with an entire space-time nested inside. The most tantalizing mysteries often lurk in the gaps between disciplines. Quantum mechanics and general relativity, the two pillars of modern physics, clash violently inside black holes. Reconciling them might require rewriting the laws of reality. revealing dimensions we've never seen or forces we've never imagined. Cygnus X-1, with its predictable X-ray flares and tidy orbits, suddenly seems almost ordinary compared to the cosmic oddities still waiting in the dark. What's exhilarating is how much we don't know. Every time we solve one black hole riddle, three more emerge. Are they time machines, gateways, the universe's ultimate recycling centers? For now, these questions hover at the frontier of science, where curiosity outpaces proof. But if history's any guide, the answers when they come will be stranger than anything we've dreamed. After all, the universe didn't put black holes in our path to intimidate us, but to remind us. The greatest discoveries often begin with the humblest admission: we don't understand. Yet, Cygnus X-1 didn't just revolutionize professional astronomy, it ignited a firestorm of curiosity among backyard stargazers and amateur scientists. When news broke in the 1970s that astronomers had found a real-life black hole, it wasn't just labs and universities buzzing with excitement. Around the world, amateur astronomers pointed their telescopes toward Cygnus, hoping to catch a glimpse of the star that betrayed the monster's presence. Most couldn't see the X-rays, of course, but tracking the black hole's companion star HD 22686 became a badge of honor. Enthusiasts logged its brightness fluctuations, noting how the black hole's gravity distorted the star's shape, subtly dimming its light during each orbit. These observations, meticulously recorded in notebooks and shared through grassroots astronomy clubs, often complemented professional research, filling gaps in data between telescope observing schedules. The rise of digital technology turned this passion into a global movement. Online platforms like the American Association of Variable Star Observers also let amateurs submit their measurements of Cygnus X-1 system, contributing to long-term studies of its behavior. When NASA orbiting X-ray telescopes caught a flare from the black hole, alerts would go out to this network, prompting volunteers to train their optical telescopes on the companion star, capturing changes that might explain the eruption. It was a partnership between high-tech satellites and backyard optics, proving science didn't always need billion-dollar budgets, just dedicated eyes on the sky. Citizen science projects took this further. Platforms like Zooniverse introduced black hole hunters, where anyone could sift through telescope data for telltale X-ray flickers hinting at new black hole candidates. Volunteers helped identify dozens of potential systems, some later confirmed by professionals. There's something poetic about a teacher in Wisconsin or a retiree in Portugal spotting pattern supercomputers missed, all because a half-century earlier, Cygnus X-1 showed the universe's darkest secrets could be uncovered by relentless curiosity. The black hole's cultural footprint deepened with public collaborations. Crowd-funded projects like Einstein at Home used idle computing power from volunteers' devices to analyze gravitational wave data, including potential signals from mergers involving black holes like Cygnus X-1. Over 500,000 participants joined, their laptops becoming part of a distributed supercomputer that's helped refine our understanding of black hole spins and masses. Even planetariums and science museums got in on the action, using real Cygnus X-1 data in interactive exhibits where visitors could steer a virtual telescope to find the black hole themselves. What started as a flicker on an X-ray detector became a bridge between academia and the public, proof that groundbreaking science isn't just for those with PhDs. Cygnus X-1 turned black holes from abstractions into something tangible, a challenge anyone could engage with, whether through a telescope, a laptop, or just lying in a backyard, staring up at Cygnus and wondering what else might be hiding in the dark. That's the real legacy of this discovery, not just expanding our knowledge of the cosmos, but expanding who gets to be part of uncovering it. Cygnus X-1 was our first glimpse into the dark heart of the universe, but compare it to something like GW 170817. The neutron star collision detected in 2017, and you realize just how far we've come. That historic event wasn't spotted through X-rays or starlight, but through ripples in space-time itself, a gravitational wave signal picked up by LIGO and Virgo observatories. The difference between these two discoveries reveals a revolution in how we explore the cosmos. Back in the 1970s, Cygnus X-1 could only be studied indirectly. Astronomers relied on its X-ray flickers and the wobble of its companion star, piecing together clues like detectives reconstructing a crime scene from scattered evidence. Fast forward to GW 170817, and suddenly, we weren't just observing cosmic violence from a distance, we were feeling it. The gravitational waves from those merging neutron stars vibrated the detectors here on Earth, translating into a faint chirp that scientists could actually listen to. It was like upgrading from a silent movie to a surround sound IMAX experience. The scale of these events couldn't be more different either. Cygnus X-1's black hole is a solitary predator, 15 times the Sun's mass, slowly feeding on its stellar companion. GW 170817 involved two neutron stars, each cramming a sun's worth of matter into a city-sized sphere, whirling around each other hundreds of times per second before colliding in a blaze of gold-forging fury. The aftermath wasn't just a black hole, it was a kilonova, a firework of heavy elements like platinum and uranium scattering across space. For the first time, we saw proof that neutron star mergers are cosmic alchemists, creating the very elements that make up our jewelry and nuclear reactors. What's astonishing is how these discoveries complement each other. Cygnus X-1 taught us black holes could hide in binary systems, while GW 170817 revealed that neutron stars could do the same, and that their mergers could birth black holes in real time. One showed us the predator, the other showed us the prey mid-feast. Together, they're revealing a universe where gravity's most extreme events aren't rare but routine if you know how to look. The tools have evolved just as dramatically. Cygnus X-1's discovery required painstaking analysis of photographic plates and analog X-ray detectors. GW 170817 was spotted by lasers measuring distortions smaller than an atom, then confirmed by 70 observatories across 7 continents, catching everything from gamma rays to radio waves. It was the birth of multi-messenger astronomy, where gravitational waves, light, and particles all tell parts of the same story. Yet for all the progress, Cygnus X-1 remains a touchstone. It's the bridge between old and new, the discovery that proved black holes were real, paving the way for everything that followed. Without it, we might not have known where to point those modern telescopes or how to interpret the chirps from LIGO. The universe's darkest secrets are still coming into focus, but thanks to that first flickering X-ray in Cygnus, we're no longer groping in the dark. We're listening, watching, and feeling the cosmos in ways its original discoverers could only dream of. NAS, a transformation of Cygnus X-1's X-ray emissions into sound, isn't just a scientific novelty, it's a haunting symphony from the abyss. Take the raw data from Chandra's X-ray observatory, where flickers of high-energy light trace the black hole's feast and map those frequencies onto audible tones. The result, a spine-tingling soundscape that oscillates between ghostly hums and sudden crescendos, each note corresponding to the violent dance of matter spiraling toward oblivion. Higher pitches represent brighter X-ray bursts, while deeper drones echo the quieter lulls between feedings. It's as if the black hole itself is whispering its secrets in a language we can finally hear. This process, known as data sonification, does more than make cosmic phenomena accessible. It reveals patterns invisible to the eye. When scientists first listened to Cygnus X-1's emissions, they noticed rhythmic pulses buried in the chaos, clues to how the black hole's magnetic fields twist and snap like rubber bands under extreme pressure. Some sequences sound almost melodic, with repeating motifs that hint at cyclical processes near the event horizon. Others dissolve into static, mirroring the turbulence of gas torn apart by tidal forces. What looks like random noise on a graph becomes a visceral narrative when translated into sound, a story of creation and destruction told in vibrations. The eeriest moments come when the sonification captures quasi-periodic oscillations, subtle X-ray fluctuations caused by clumps of material orbiting just outside the point of no return. These translate into phantom chimes, their tones shifting higher as the gas accelerates toward light speed, then vanishing abruptly as it crosses the event horizon. It's a chilling audio representation of matter's last cry before disappearing forever, a sonic tombstone for atoms stretched beyond recognition. But this isn't just about atmosphere. Sonification has practical stakes for researchers. Blind astronomers, for instance, can now hear black hole activity with the same nuance as sighted colleagues viewing spectral graphs. The technique also uncovers anomalies, odd harmonies, or discordant notes that might indicate rare phenomena, like a star being swallowed whole or jets of plasma firing unexpectedly. When the Event Horizon Telescope captured its iconic black hole image, sonification added another dimension, letting listeners trace the glowing ring's asymmetry in pitch variations that mirror its brightness. What's profound is how these sounds bridge the abstract and the emotional. Cygnus X-1's growls and shrieks make its violence tangible, transforming equations into experiences. A generation raised on sci-fi black hole sound effects, usually Hollywood's dramatic whooshes, can now encounter the real thing, a dissonant, unsettling chorus that defies expectation. There's no soundtrack in space, of course, but these sonic interpretations remind us that the universe's most enigmatic objects don't just bend light. They compose their own dark music, waiting for us to press play. Black holes aren't the universe's only possible solution to gravity's ultimate victory. They're just the most terrifyingly elegant. Imagine a cosmic compromise where matter doesn't vanish into a singularity, but instead forms a bizarre bubble of exotic energy. That's the premise behind gravastars, one of several theoretical alternatives to black holes dreamed up by physicists uneasy with the idea of infinite density. These hypothetical objects would mimic black holes' gravity and light-trapping effects, but replace the event horizon with a shell of ultra-dense matter, like a cosmic egg with a yolk of vacuum energy. From afar, even a telescope might struggle to tell the difference, yet Cygnus X-1 stubbornly refuses to fit these gentler models. The smoking gun lies in its X-ray emissions specifically, the way matter behaves just before vanishing. Gravastars predict a softer transition, with gas piling up against their theoretical shells. But Cygnus X-1's accretion disk shows matter accelerating to relativistic speeds, then abruptly cutting off as if falling through a trapdoor. That sudden silence matches Einstein's predictions for an event horizon perfectly. Even more damning, the quasi-periodic oscillations in its X-ray flickers, rhythmic pulses caused by clumps of gas orbiting at near light speed. These patterns align precisely with simulations of material spiraling into a black hole's gravity well, not bouncing against some exotic barrier. Then there's the star. HD 22686 orbits Cygnus X-1, as if tethered to an invisible wrecking ball 15 times heavier than our Sun. Gravastars and other alternatives struggle to explain how such a dense, dark object could exist without collapsing under its own weight. Some theories, like boson stars, hypothetical objects made of ultralight particles, could theoretically reach black hole-level mass, but they'd shimmer with detectable quantum vibrations. Cygnus X-1, utterly silent beyond its X-ray din, a perfect vacuum of extra emissions. Even the black hole's shadow, as glimpsed in the Event Horizon Telescope's later images of M87, seals the case. The lopsided glow of its accretion disk matches simulations where light bends around a spherical event horizon, not some alternative structure. Gravastars would distort that signature, warping the shadow's shape in ways we simply don't observe. It's as if the universe took one look at these theoretical contenders and said, Nice try, but watch this before unleashing Cygnus X-1's flawless performance. What's fascinating is how these dead ends sharpen our understanding. Every alternative ruled out, whether gravastars, boson stars, or naked singularities, forces physicists to refine black hole models further. Cygnus X-1 isn't just a black hole because it fits Einstein's math. It's because after 50 years of scrutiny, no other idea explains its brutality so completely. The universe, it seems, prefers its monsters uncompromising. Want to explore Cygnus X-1's gravitational grip without getting spaghettified? NASA's Eyes on Exoplanets lets you take a virtual spaceship right into this binary system with accurate orbits based on real astronomical data. As you approach, watch how the black hole's gravity warps your trajectory, bending light from its companion star in real time. The best part, you can tweak variables. What if Cygnus X-1 were twice as massive? What if you replaced it with a neutron star? Seeing these cosmic forces play out visually makes abstract concepts like tidal forces and accretion disks click in ways equations alone never could. For hands-on experimentation, Universe Sandbox 2 transforms your computer into a celestial playground. Drop black holes near stars and watch them tear each other apart, or recreate Cygnus X-1's exact mass ratio to see why its companion star hasn't been fully consumed. The simulation shows how the system's 5.6-day orbit creates predictable X-ray flares mirroring what real telescopes observe. You can even simulate gravitational waves from black hole mergers, connecting the dots between Cygnus X-1's quiet feeding and the violent collisions LIGO detects. If mobile's more your style, try Space Engine. Swipe through the Milky Way until you find Cygnus constellation, then zoom in on HD 22686, the supergiant that betrays the black hole's presence. The app uses Gaia mission star maps for pinpoint accuracy, letting you witness how the star's teardrop shape distorts under its invisible partner's pull. Toggle between visible light and X-ray views to see why astronomers needed specialized detectors to spot this cosmic predator in the 1970s. For the coders and data enthusiasts, Python libraries like Astropy offer tools to analyze real Cygnus X-1 observations. Download light curves from NASA's HESARC database and write scripts to detect orbital periods or model accretion disk temperatures. Jupyter notebooks from GitHub communities walk you through calculating the black hole's spin from X-ray flicker patterns, the same techniques professional astronomers use. It's like having an open-source radio telescope on your laptop. Educators and students will love the Black Hole Encyclopedia from the Harvard-Smithsonian Center for Astrophysics. Their interactive Build a Black Hole tool lets you adjust mass, spin, and accretion rate to recreate Cygnus X-1 specs, then compares it to other known systems. The time dilation calculator is a specially mind-bending input how close you'd orbit, and it shows how minutes near the event horizon could equal years back on Earth. These aren't just toys, they're simplified versions of the same modeling software used in research papers. The thrill of these tools isn't just in playing God with virtual cosmos, it's in discovering how much you can learn by tinkering. When you manually adjust Cygnus X-1's parameters and watch the system destabilize, you internalize why real black holes behave the way they do. That wobbling star isn't just an abstract concept anymore. It's a dance partner you've seen stumble when gravity's rules change. Whether you're a curious teen or a retired engineer, these simulations make one of the universe's most mysterious objects feel almost approachable, almost. Cygnus X-1 wasn't just the first black hole we found. It was our universe handing us a key to a door we didn't even know existed. Think about how much has changed since that faint X-ray flicker in the constellation. Cygnus rewrote the rules of astrophysics. Back then, black holes were mathematical phantoms, debated in lecture halls but never touched by evidence. Today, we've heard their collisions through gravitational waves, photographed their shadows, and even turned their deadly feasts into soundscapes. And it all traces back to this unassuming binary system, 6,000 light-years away, that dared us to believe the impossible. What's remarkable isn't just how much we've learned, but how Cygnus X-1 keeps surprising us. It taught us black holes could exist, then pushed us to ask how they spin, how they feed, how they warp time itself. Every new telescope, every supercomputer simulation, every daring theory owes something to that first discovery. The Event Horizon Telescope's stunning image of M87's black hole. That technology stands on the shoulders of the scientists who spent decades decoding Cygnus X-1's X-ray whispers. The chirp of merging black holes picked up by LIGO, that sound was predicted by equations tested against this very system. Yet for all our progress, the most thrilling realization might be how much remains unknown. Cygnus X-1's companion star still pours fuel into the abyss, its fate a ticking clock we're only beginning to understand. The black hole's jets, its spin, even the quantum mysteries at its event horizon. Each observation peels back another layer, revealing deeper questions. And that's the true gift of this cosmic pioneer, not answers, but an endless supply of puzzles to chase. So where do we go from here? The same place we've always gone forward, armed with curiosity. Maybe you'll be the one to solve the information paradox, or capture the first video of a black hole's accretion disk in motion. Perhaps you'll design the telescope that spots primordial black holes from the dawn of time. The tools are better than ever, but the spirit's the same as it was in 1971. Look closer, ask why, dare to imagine, because Cygnus X-1 wasn't the end of a mystery. It was the first note in a symphony we're still composing, proof that the universe saves its darkest corners for those brave enough to shine a light. And if history's any guide, the next breakthrough won't come from someone who has all the answers, but from someone who, like those early astronomers, isn't afraid to stare into the void and wonder what else might be